Hey folks, we're going to do solubility product constants. Heavy into math here. Pull out your calculator. Some are easier than others. Bottom line, folks, is you've got to be able to think through these. You've got to logically reason through them and understand them. Okay. Given the concentration of sodium ions and chloride ions, they're both 1.90 for the dissociation of sodium chloride. So we think about this. This is going to be NaCl, which is a solid. We ignore solids, remember? And they become Na plus and Cl minus, and those are both aqueous, and because they're aqueous, we're going to actually worry about them. So our solubility product constants, KSP, the way they typically work is it's the concentration of the products only, because the concentration of the reactants don't matter because they're solids. Alright, so we don't have to worry about those. Right, and we're told that they are both 1.90. Now that's what you would expect because there's a one-to-one relationship between them. If the relationship were different, then you'd see that it would be twice as much or 3 times as much as whatever, and we'll see that in the next problem. Anyway, so we have 1.90 times 1.90, and that gives us an answer of 3.61, and that's our solubility product constant. Notice there are no units on this. Alright, let's go and think about calcium hydroxide, CaOH, and you got to think about it because it's CaOH2, because calcium has a +2 charge, hydroxide has a -1, so it becomes Ca with a 2+ charge, and hydroxide with a 1- charge, and those are aqueous. So this is where your coefficient comes from. So it's very important to be able to do those. Okay, so now our KSP is going to be 1.08 times 10 to the -2 times 2.16 times 10 to the -2, and that's going to be squared. Why? Because there's a 2 coefficient over here, so that 2 coefficient goes down here. And you should notice, by the way, that there's a difference between the 1.08 and the 2.16, and the fact is that the second one is double the first one. Well, why is that? Well, it's because whenever you have calcium hydroxide and it decomposes, for every 1 mole or for every 1 molecule of calcium hydroxide, you're going to end up with 1 calcium, but you're going to end up with 2 hydroxides. So as a result, the hydroxide is going to be twice as concentrated as the calcium when it dissolves. All right, when I actually go and plug this in and multiply it out, I get 5.04 times 10 to the -6th. And again, there are no units for solubility product constants. All right, now this one's a little bit harder. Now this one you got to think through. Given the solubility product constant for barium carbonate is 2.58, barium carbonate. Barium is a 2+, carbonate's a 2-, so it breaks apart into barium 2+, and carbonate 2-. Right? What's the concentration of each of the ions in this solution? That's interesting. How would you figure that out? Well, we know that our solubility product constant is going to be 2.58 times 10 to the -9th. And that is going to be the concentration of barium 2+, which is aqueous, times the concentration of CO3, which is 2-, and it's aqueous. So how do we do that? Well, if we look at this as x, if we take each one of these as just x, right, this is going to be x times x, or x squared. So 2.5 times 10 to the -9th is equal to x squared, which means the square root of 2.5 times 10 to the -9th is equal to x. So you can sit down and plug that into your calculator, right? And you will, this is 2.58, by the way, every single time. If you take the 2.58 times 10 to the -9th and you take the square root of it, you will find out that that's 5.08 times 10 to the -5th. So that is the concentration, that's the molarity or concentration of the barium and the carbonate. Right? So that should be this number, and it should be this number. Well, how do you check your work? Well, you take this number and you multiply it by itself. You square it, and it works. So if you check your work, you'll find out it works. Okay, given that the solubility product constant for barium nitrate, let's do this again. Barium nitrate. Ooh, this is going to be tricky. Barium nitrate, right? And this becomes Ba, the concentration of Ba 2+, which is aqueous, times the concentration of NO3, which is 1-, and that's 2 of them. Oh, sorry. I apologize. I should have written that as just an equation. Ba NO3 2 becomes barium 2+ plus 2 nitrates 1-. Right, so that means your solubility product constant is this stuff up here. So your KSP, which is given to you as 4.64 times 10 to the minus 3, is equal to the concentration of your barium times the concentration of your NO3 squared. So what can we figure out here? Well, there are a couple of pieces to put together. Well, the first piece you need to know is when barium nitrate breaks apart, if I take the concentration of barium as being X, then the concentration of the NO3 is going to be 2X, right? Because the concentration of nitrate, you get twice as many nitrates as you get barium when it decomposes or it dissociates. So this is going to be, this number is going to be X times 2X squared. 2X squared. So that's equal to X times 4 times X squared, which is equal to 4X cubed. So assuming that I did my math right to come up with 4X cubed, then I take the 4.64 times 10 to the minus 3, and I divide that by 4, and that's going to give me X cubed. Right? So that gives me 1.16. 1.16 times 10 to the minus 3 is what X cubed is. So what do I have to do? Well, I have to take the cube root. X is equal to the cube root of 1.16 times 10 to the minus 3. Right? So if I do that, then that becomes the cube root is equal to 0.105. So that is the concentration of barium. And that means the concentration of nitrate has to be twice that, because there are twice as many nitrates as there are bariums. So that's going to be 0.210. That's equal to 0.210. Really? After all that math, does that really work? Well, let's find out. How do we find out? Well, we plug it back into this equation. Right? Our KSP is supposed to be equal to the concentration of barium times the concentration of nitrate squared. So that is 0.105 times 0.210 squared. And if I do that, I come up with 0.00463, which is certainly close enough to my answer of 0.00464. So that works. I've checked my work to make sure it's right. So that's cool. On to number 5. All right. You're given a saturated cobalt-2 carbonate solution, and the molarity of each ion is 1 times 10 to the minus 5th. Let's see. Cobalt carbonate, CoCO3, that's plus 2 minus 2, so it just breaks up into cobalt with a 2 plus charge, and carbonate, which has a 2 minus charge. They're both aqueous, so when I do my solubility, it's going to be the two of them times each other. So it's 1 times 10 to the minus 5th times 1 times 10 to the minus 5th. Nobody has to be squared or cubed or anything. So it's 1.00 times 10 to the minus 10th is my answer. All right. Let's try aluminum hydroxide. Molarity of aluminum. Determine the solubility product constant. So I didn't get the concentration of hydroxide, but I should be able to figure it out. And how can I do that? Well, aluminum hydroxide is AlOH3. Why is it 3? Well, aluminum has a +3 charge, OH has a 1-. So that becomes Al plus 3 OHs. All right, and so that means my concentration here is 1.83 times 10 to the -9th. And that means the concentration of my OH, for every aluminum hydroxide that dissolves in water, I get 1 aluminum ion, but I get 3 hydroxide ions. So the concentration of my hydroxide ion has to be 3 times that number, which is going to be 5.49 times 10 to the -9th. All right, so how do I figure out my KSP? My solubility product constant is equal to the concentration of my aluminum times the concentration of my OH raised to the 3rd power, which is going to be 1.83 times 10 to the -9th times 5.49 times 10 to the -9th. This is going to be a very, very small answer, because -9 times -9 times -9 is going to be like times 10 to the -27th. So this is going to be a very, very small number. All right, and I had to take another -9 on top of that, so it's going to be 3.03 times 10 to the -34th. That's a very, very small solubility constant. Okay? All right. Next one. Okay, this one is a lot like number 3 earlier. You're given the solubility product constant. You have to work backwards. But this is kind of a simple one because it's copper chloride. It's copper 1 chloride. So that's CuCl, which is going to become Cu with a 1+, and Cl with a 1-. Those are both aqueous. Right? So my KSP is going to be the concentration of the copper ion and the concentration times the concentration of the chloride ion. And I know what my KSP is. So if 1.72 times 10 to the -7th is equal to the concentration of Cu plus times the concentration of chlorine minus, chloride minus. Okay, so what does that tell me? Well, that means that if I take whatever number, these two numbers have to be the same. So this is, if I treat these as x, that's like x squared. So if I figure out what x is, I have to take the square root of this. So the square root of 172.1.72 times 10 to the -7th, okay, is equal to 4.15 times 10 to the -4th. All right. Now, do I believe this number's right? How can I check it? Well, you just plug right back in here and chug through your calculator. So you'd say 4.15 times 10 to the -4th times 4.15 times 10 to the -4th. All right, what do you get? Well, you get 1.72 times 10 to the -7th, which is what you started with. So that's great. So it works. All right, last problem. A little bit more complicated. We're talking about copper 2 hydroxide. So this is copper 2 hydroxide, so it's CuOH2. You can see where this is going, can't you? All right, so it becomes copper with a 2+ charge plus 2 hydroxides with a 1- charge. These are both aqueous. Right, and we know that our solubility product constant, which is KSP, is equal to the concentration of copper times the concentration of hydroxide squared. Right? So let's see, we know that the concentration of copper, again, if we take that as x, this is going to be 2x. So the concentration of hydroxide is twice that of copper. So this is going to be x times 2x and that entire thing squared. So let's see, that's going to be x times 4 times x squared, which is 4x cubed. So I have to divide the solubility constant by 4. So 4.80 times 10 to the minus 20 divided by 4 is equal to 1.20 times 10 to the minus 20. All right, so that is equal to, come here, pen, thank you, it's equal to x cubed. So I have to take the cube root of 1.20 times 10 to the minus 20. All right, and if I take that cube root, sorry, switch to the next page. If I take that cube root, I come up with 2.29 times 10 to the minus 7th. And that should be my concentration of the copper ion. So it should be 2.29 times 10 to the minus 7th. And then what I would have to do to check my work is I have to look at the OH ion, which is going to be twice as concentrated, so it's going to be twice that number. So that would be 4.6 would be 4.58 times 10 to the minus 7th. And that's your concentration of the hydroxide ion, but I have to square that, remember, because this coefficient that's in front of it, which is 2. Right? And if I do that, I come up with exactly what I started with, times 10 to the minus 20, which is perfect, because that's what I want to make sure of. That's how I check my work. Okay, so the concentration of my copper ion is this, and the concentration of hydroxide ion is the 4.58 times 10 to the minus 7th. All right, folks, that is it. If you have questions, please come see us in class. We'll help you out. Take care.